All right, new content, new year, new us, new content. So here we go. Good news, bad news. Okay, it's the same thing. Okay, it's that this chapter is really just kind of an extension of a previous chapter. So that's great news if you felt like that went well, and it's bad news if you felt like that did not go well. Now, the other great news for everybody is even if it didn't go well, this gives you more afforded practice in that exact same sort of area, but we are kind of highlighting something different. In order to practice with that, here's what I'd like you to do. I've done this in the past where I've just asked everybody, but that doesn't make it as personal as I'd like it to be, so here's what I'm going to do. I'm going to put 3 things up on the board. I just want you to cover all of that in your group. We'll cover it together in order to best understand these concepts and then lead that into the new thing from here. So, okay, the first conversation I want you to discuss is this. Scalar versus vector. What's the difference and why is the difference? Number 2, Newton's 3 laws. And number 3, the 2 properties of mass. Discuss in order in your group. In order, ideally. We'll be right back after these messages, people online. Yo!
She keeps on bleeding.
Have you tried positive conversation?
No.
Quit it! Just look at your boo-boo and yell quit it.
Well, because I thought it was done. Is a measurement with no direction, so it's not here.
Can you give an example?
Thank you. A car, a speedometer. Wouldn't a speedometer work? When you're driving a car, it only looks at how fast it goes.
Speedometers are weird examples. Displacement velocity are weird examples because they have both. So try to pick, when you're giving an example, try to pick something. Right, so try not to pick something that could technically, so speed is the scalar, velocity is the vector, distance is the scalar, displacement is the vector. So when giving examples of scalar, try to choose something.
You missed, actually.
I know, I saw it hit a poster right there. On this again.
You did.
So embarrassing.
Oh, you got it. Like, you got it that time. 3 times later.
The attraction between any 2 masses is like
Favorite story with this thing? I didn't bring this out all year one year. It's about 2-3 years ago. And then during a lab, like the last lab in the year, I don't know why I did this, but I picked the perfect person. And she was faced that way, and I did.
there was like a spirit.
She like freaked out. I saw her look around and not say anything. And I did her like to it, and I would do it, and it takes travel time, so you can like put us underneath if you go a decent enough distance. And so I did that, and the funny thing was I would wait for her to look back, and everyone else in the class watched me do it at that point in time. Like, they all saw what was going on, and then on the 3rd time, her reaction was perfect. She goes, "You guys, there is a presence in here. I don't think you understand. It has hit me on the shoulder like 3 separate times." And she went full bore on it. It was fantastic. Other fantastic thing is because there's travel time, you can hit somebody in the hallway as they're passing by, right? And so I would do that, and then I would step to the side, so students, normal students, just looking like they normally would out here, so they could watch the hallway. And we hit someone walking by. That's how they responded, and they had no idea where it came from. It was.
That was a cute little demonstration there.
That's what they did.
Can I do that? She just went off scared.
All right, that's right. I distracted you. Keep going.
I think we're done.
You done? You sure?
No.
No. Yeah. I think next song I'm going for is Zelda's Lullaby.
Guys, I got one of the
You song of storms.
Spading already. One of them was
What?
You should play the Hobbit. You should play the Hobbit theme on that.
The Hobbit theme. We see mountains. Or which Hobbit theme?
The Shiny.
Here we go. All right. Let's start scalar versus vector. What's a scalar? What's a vector?
I don't care about direction.
Okay. What doesn't? Scalar. So give me an example. Don't use one of the examples that can do either. Don't use one of the examples that can be either. Don't use one of the examples that can be
I
either.
just got freaking yelled
Yes.
at over it.
Temperature.
Temperature, yeah. It's like literally every number that you calculate ever. There's less people in here. It is colder in here. These are measurements of scalar. That thing weighs less. Weight is weird. I'm sorry. That one has less mass. Okay, because mass is scalar, but weight weirdly is a vector. Blah, blah, blah. Okay, we have 4 examples of vectors. What are they?
10 meters west.
Okay. Yes.
12 miles.
What are we measuring there?
Distance and direction.
No. So what are we measuring there?
Distance.
No.
Displacement.
Displacement it is. There are 4 vectors. The first one, there we go. Displacement. What does it mean if displacement is right? What does that mean? What's going on in the situation?
You're moving 10 meters.
Positive way.
Okay, I like that. Or if you look at its definition is final minus initial. Or simply put, that the final is to the right or more positive than the initial. Do you have to be on a positive position in order to have had a positive displacement? Absolutely not. You can go from -8 to -2 because that would be moving in a positive way. All right, next. What is another example of a vector? We've got 4 that we've discussed.
Delta T. Final.
That would not be a vector. What is delta t?
Oh,
That would be time. Correct. Time is not a vector. That's a scalar. As we only understand it right now, it only goes one way. Okay. We'll get to when it goes the other way later. All right. What's that? Velocity. Correct. So here's a velocity vector pointed to the right. Notice one very important thing. Whenever we discuss vectors, what shape is always going to be? What should immediately come to your brain? What's the first? You've seen me do it now twice. Arrows. Correct. Vectors, simply put, arrows. I should have used the same color. There we go. Arrows. There we are. All right, next. What does it mean then if velocity is to the right? Well, look at the definition of velocity. What's the definition of velocity?
Displacement over changing time.
And if you look at that definition, what you can simply put is that actually displacement and velocity go really nicely in hand with each other. What does it mean if velocity is positive? Well, over here I have displacement divided by a scalar. So what does it mean? If displacement's positive, then velocity is going to be positive. What does it mean if velocity is positive? I'm going right. I'm traveling right in a particular amount of time. Next, what is the next vector? Acceleration. Are you just looking on the board because we did it earlier?
No.
Oh, it is over there.
Well, we've already seen it.
Hey, you can stop right here. Oh, I don't care about that.
Yeah, I know.
Jeez. All right. So fair enough. I'll switch them.
I think
I
that
use my
was
resources.
there is a presence in this
There's
room.
a presence in this room. His name is Spainhour. All right. What is the definition of acceleration? This is where it starts to get a little bit interesting because while velocity will absolutely go the exact same direction as displacement, does acceleration have to go the exact same way as velocity? No, because it's looking at how velocity changes. So what does it mean if acceleration is to the right? No, not inherently.
Wait.
Say that differently and you're good. I'll start you off. Velocity is... Come on, I just said it. Changing to the right. The definition of acceleration is the change in velocity over time. Okay, so let me read this out for you so you guys can see it for the future. The definition of velocity is the displacement over time. So if displacement is to the right, then velocity is to the right. So what does it mean? Acceleration is the change in velocity over time. So what does it mean if it's to the right? Then velocity is changing to the right. So why does that not inherently mean it's going to speed up? Well, I'll demonstrate. Here we are. Here's me starting at rest. What's going to happen in order for my velocity to go to the right? Yes, I will speed up in this case, as my velocity, which is pointing to the right, is increasing to the right. But in what scenario would that not occur? What if I already have a velocity this way? What if I'm walking this way? What is going to happen? What's going to happen if my velocity changes to the right? I will slow down to stop. It means the change is that way. This is an important thing for in 2 chapters, really understanding these fundamental understandings. Okay, what is the last vector? Force is correct. Let's go purple in this. What does it mean if force is to the right?
Yeah.
So you're close, but keep in mind what you're struggling. What I would take issue with there is this would be the definition of a single force. Does a single force pointed to the right mean I'm going to accelerate to the right? No, because what decides the direction of acceleration? Not a single force, but a sum of all of the forces together. So what does it mean if a force is to the right? Well, simply put there, a force is a push or a pull. Something's pushing right, something's pulling right? This could be if one person is shoving Colin to the right, but somebody equally is also annoyed at Colin but wants to shove him to the left. It is a combination of both of them that decide. Now, if there is only one force, then which way are they going to accelerate? That particular way. Interesting thing I actually realized for like the first time last hour, and maybe it's dumb that I realized this for the first time last hour. I've always said that these two go together in direction, and I've like known this independently, but if there is only one force, these two also perfectly match in direction as well. All right, let's go to Newton's 3 laws. What is Newton's first?
Constant velocities and balance forces.
Okay, there are 3 things. Yes to everything you just said, by the way. You're not wrong. There are 3 things that I highlighted when doing these laws that can really be kind of gotten down to 2, and really it's what you just said a second ago. But the 3 things we mostly focused on were velocity, acceleration, and forces. Let's begin with forces first because you already had it. But I think we're just kind of putting a bow on what you said. What's true of forces for first law? They're balanced. How do I write that? How do I write mathematically that forces are balanced? Sum of forces is 0. Okay. The second thing that so I'm going backwards with this because usually when I first teach it, I go velocity, acceleration, and forces. And the reason I teach it in that particular order is because you just walked out of kinematics. You're much more familiar with them. Okay. Although you're doing it right, this is the better way to explain them because it's kind of cause and effect. This is the cause, then what's the effect? Well, the effect is what's true of acceleration then? 0 meters per second squared. Now, I'm not going to write the third thing up there because if I've written that, you should already know the other thing up there. And the other thing up there is what's true of velocity then, if that's the case. Constant, yes. So the 3 things we covered were velocity, acceleration, and sum of forces. But really, it's just 2, cause and effect. The cause is if forces are balanced, then it won't accelerate. Now, here's an interesting thing that we might have talked about once or twice before, but it's definitely going to play out today. This is colloquially known, most people know this as Newton's first law of what? Inertia. So this carries with it inertia, which is measured by? What measures inertia? Mass. But what's weird about that being called Newton's first law, by the way, it absolutely should be. It's not wrong that it's called Newton's first law of inertia because they're perfectly representing inertia, how they're traveling at a constant velocity. What's weird about it is this. Let's imagine you're in space and a bowling ball is flying at you. And right next to the bowling ball, traveling the exact same velocity, is a tennis ball traveling at you. Are both of them following Newton's first?
Yes.
Yes. And their motion is identical. Do they have the same inertia? So you don't actually see the manifested effects of their inertia in Newton's first law. Even though it's called Newton's first law of inertia, you don't see the effect of inertia in first law. You don't see it until what happens? AKA when it hits Newton's
Second law.
second law. Let's knock that out. What's Newton's second law?
Changing the velocities and balance forces.
Correct. And what's the equation that we could write that covers all of this? Mass times acceleration. There is all of the stuff worked into one equation. The first thing is let's knock out those 3 things again. What's going on with velocity? What's going on with acceleration? What's going on with force? Let's do it in the opposite order. You've already said it. What's going on with force that we're covering second here? What's true of forces in second? Unbalanced. Okay, what's true of acceleration? Oh. There's a probably best way to say it. It's kind of weird because there is acceleration as opposed to the previous no acceleration. And then finally, what's happening with velocity? There's the one. That's the one that is specifically changing. Okay. So that covers that really by getting rid of this right here. These two are proportional is really what is said that kind of covers that right there. So why the whole equation? Well, it kind of comes back to this. We don't see inertia until right there. That is the property of inertia. What mathematic thing happens because of the inertia? Get the bowling ball and the tennis ball coming at you, right? Let's say you put out a certain amount of force to stop the tennis ball. Okay, at the same time, you decide, foolishly, to use the exact same amount of force on the tennis ball as you do on the bowling ball. What's the problem? The bowling, because? Bowling ball is going to, so what's going to happen here? Bowling ball, because it has more mass, will, not quite, because I'm using the same force, I said. So if I use the same amount of force to stop the bowling ball and the tennis ball, it will have less acceleration, which means probably, yes, it probably will run into me because I probably won't have enough time before it hits me. Does that make sense? Or, obviously more logically, if I don't want the bowling ball to hit me, I want to give it the exact same acceleration as the tennis ball. So what do? You increase the amount of force. You have to take more force to stop the bowling ball than you did the tennis ball because it has more inertia, so it takes more oomph to stop. Yes? So this right here is where you actually see inertial mass represented in Newton's second law. And as we did a ton last chapter, what we said is, hey, we don't really need to package all of this up differently because we would just start right here. And then what simple thing would happen would you not? I'm trying to draw on you. What simple thing would happen at the beginning of the problem if it followed first law instead? Yeah, because acceleration was 0, that would cancel out and would take us from this straight to that guy right there. So boom, first law was packaged nicely in second law. Cool beans? Cool. This chapter focuses basically on these exact same principles, except the focus, instead of being on first law and second law, is now on third. What's third law?
For every force, there's another force that is equal.
Yes to both. For every force, there's an equal opposite force in the opposite direction, and the mathematic way to write that is? Okay, and essentially what that says, by the way, is not 12 and 21. It's saying, yes, the force of object 1 on the second object is equal to the force of the second object back on first, but they should be in opposite directions. If you high-five someone else, you will give each other the exact same amount of force. If you high-five a small little 3-year-old, the same amount of force that you would give to another full-grown adult, right, they will give you the exact same amount of force back, which will not probably move you very much. We'll not talk about them because of Newton's second law right here. So we're going to primarily try to get to this guy right here. Now, sadly, that won't happen until tomorrow, but that is, in fact, the goal of this. We are not so much worried about what happens to an individual object, sort of, because we are kind of today, but we're going to worry about what happens to a combination of objects a little bit. But I'm missing one more subject matter, but we've really already hit one of them. The two properties of mass, we really kind of spent already ad nauseum on one of them, which was inertia. So what's the second property of mass?
Gravity.
The only thing I want to add to the gravity conversation is simply this. I showed you where you find the property of mass in equations. Where do you find the property of property of inertia in equations? Where do you find the property of gravity? What equation gives us the property of gravity? Almost. Fg equals m. G, correct.
My bad, sorry.
That guy right there. Yes. That is the property that's the equation where you will see gravitational mass. This is the equation where you'll see inertial mass. Every mass that you see in a problem will come from one of the two of these right here as we continue forward. All right, new content. Here we go. Momentum. I always hesitate to throw out words, especially ones that you already know, because there can come with it, kind of like, oh, I got this already. Careful with that. But momentum is usually one that's at least far enough away and relatively done correctly that I don't have too much issue covering. Okay? And really the reason for momentum comes down to a conversation we just had between first law and second law and the problem of inertia. If I am walking next to my 4-year-old child and we are traveling at the exact same velocity, will it take the same amount of oomph for someone to stop us? Absolutely not. Okay? Now, would we notice that, coming back here, in first law? No, we don't see that in first law. We don't see it until second law. But what would we share? Well, let's not start off with me and the kid. Let's start off with the tennis ball. Let's go to the example in space. Here's a tennis ball and a bowling ball coming at you. Both of them are going at 2 meters a second. But of course, it's not going to take the same amount of oomph to stop both of them. So what do? Well, I've got velocity here. By the way, since it's a velocity, this new thing that we're talking about, is it probably going to be a vector or a scalar? It's probably going to be a vector. We are going back to vectors. Keep in mind that we hit vectors in 1D kinematics and 2D kinematics and forces, and then in energy, we kind of like to skip out on it for a while. So there are some practices that you might have forgotten about that we'll get back to here. But simply put, velocity is going to the right, so this thing is going to the right. All I want to do is add in its inertia. For sake of argument today, these numbers aren't quite perfect. Let's say that the mass of a tennis ball, this is the one that's too big, is about 0.5 kilograms. It's way too big. It's like a pound tennis ball. Don't ever use a tennis ball that is this big. But we're going to try to keep our numbers relatively similar. And the mass of Sally, this one actually is relatively accurate, of the bowling ball is 5 kilograms. Now, what does that mean? Well, what it means is, since this has 5 and this has 0.5, Sally has 10 times the amount of atoms and therefore should be 10 times as hard to stop. But just looking at these two vectors of velocity, you would not notice that. So simply all we're going to do is scale up that vector of velocity with mass. Specifically, if you had to guess what property of mass, inertia, correct. And this, let's use a different color here. Let's use this like neon bluish. This, when multiplied out, this would be 0.5 times 2. So actually I get 1. And then this 2 times 5 would get me 10. And I would see from this vector, just visually I can see from this vector, that this guy right here, this bowling ball, is 10 times harder to stop than this tennis ball, even though they are going the same speed. Is it possible that I could get the tennis ball and the bowling ball to have the exact same momentum? Yeah. Simply put, what do I have to do? What has to be true of the tennis ball in order to have the exact same momentum? How much more? 10 times. Since it's 10 times smaller, I would just have to throw it 10 times faster. And if I threw it 10 times faster at 20, then it would also have a momentum of 10. Does it make sense that the tennis ball thrown 10 times faster would be just as hard to stop as a bowling ball thrown 10 times slower? Hopefully, yes, it should make sense that that kind of tracks. Now let's talk some units and some variables here for starters. All right, you'll notice I didn't give a variable to momentum yet. Maybe you already know what it is. This is the first time, I think it's the first time, where I would argue the variable makes as little sense as possible. The reason for this new variable is simply that mass was already taken as m, so it doesn't make sense to do another m. So the letter that we use for momentum is p. It is because of the Latin word for it, standing for progress, but simply put, momentum is the vector p, and it is a vector. Velocity is a vector. Remember, you don't have to put that equation in the thing. That's all that that says, is that it's a vector, and momentum is a vector. Let's talk units real quick. What should the units for momentum be? Kilograms, meters per second. Now, this is the first time, usually, when we have done, like, say, for example, coming back here, when we did this for newtons. What is force? Well, it's a kilogram times a meter per second squared. Don't want to write that all the time. Let's call it a newton. Then we had newtons times meters. Don't want to write that all the time, so let's call that a joule. Then we had joules over seconds. Don't want to write that all the time, so we call this a watt. We do this all the time in physics, except right now, I don't know why, we didn't. Those are the units that we will be using for momentum, kilograms times meters per second. Maybe it's because so often momentum gets separated out into its individual parts. You kind of need to think about momentum as a combination of two things, right? If a linebacker from a professional football team is coming at you, right, you do have to consider both how fast and how big they are, right? If Spainauer wanted to have the same momentum as one of them, what's he probably going to have to do? Run faster. Run faster, yes. All right. Sadly, not that much faster, but yes, faster. All right. So great. What does momentum do for us? Well, like I said, what it does is it combines together two of the things that we really want to focus: the motion of an object with how hard it is to stop the motion of an object. How do I understand what this number means? By the way, I should go back and give units to this. I purposely didn't put them on here, but this is the units of the tennis ball is 1 kilogram meter per second and 10 kilogram meters per second. One really helpful thing when you get into a new concept is like understanding what that number really means. And the best thing that you can do is try to take something that you like regularly use to put in context. So, for example, what is the mass of a fairly kind of standard human being? Somewhere, like obviously it's a little bit varied, but what's a relatively normal mass? Yes, we've done this in here quite a few times. 80, okay, so to give you an idea, about 80 is about 180 pound person. 70 kilograms, like a 150 pound person, right? Obviously 60, you're starting to get down to 120, 130. A 100 kilogram person is about 220 pounds. Obviously we can scale this all the way up using their gravitational mass to figure out what their inertial mass is, blah, blah, blah. But, okay, so let's say our range is somewhere between a 130 pound person and a 220 pound person, whatever. Obviously that goes from 60 up to 100. Okay, so you can kind of choose your numbers as you see fit in here. Let's say 80, just to call it average. 80 kilogram person. How fast does a normal person walk down the hall all the time? In meters a second, roughly.
Too slow.
Too slow, correct, but I need numeric. 2 meters a second is kind of fast. You're kind of speed walking a little bit. As you said a second ago, they're not moving 2 meters a second, but 1 meter per second, probably within that 1 to 2 range. So giving a range to that from slow to fast, given from big to small, your lowest range on a human is something like 60 kilograms meters per second. Okay, your high range on that, if you have a 220 pound person booking it to class, is about 200 kilograms meters per second. Now, I'm walking next to my 4-year-old kid. Do we have the same momentum? No. What could he do, though, to have the same momentum? Run faster. How much faster does he have to run from me? Whatever the opposite of the ratio of our inertias. I think he's roughly about 20% of me right now, sadly speaking. Well, he's probably gotten another 4-year-old different. He's probably closer to about 30% of me right now. Let's do math easier, though. The 2-year-old's probably 20%. So 1/5 of mine. So how much would the 2-year-old have to go faster in order to get the same velocity? 5 times faster. Right. Then, if the 2-year-old's coming at you 5 times faster than I am, and you have to stop both of us, what's going to be true of the amount of force you got to use? Same in both cases. All right, that being said, let's go to force real quick. I mentioned a second ago that we are going to be focusing on third law. You're going to see that happen a lot tomorrow, but we are actually going to start in second so we can understand a very important thing about momentum. So let me just start writing up here Newton's second law. What was it again? It's Newton's second? All right. Do you see momentum at all in that? Probably not yet, but what could we kind of
See the mass.
expand? I see mass. What's acceleration? Change in velocity. So I could make this sum of forces equals mass times change in velocity over time. I'm going to go the long way around with algebra because, quite frankly, I think some of you can already spot the conversation right here. Okay, I'll do an off-board. I'll come back over here in a second and show you kind of the quickest way to do this, but I want to show you a few things along the way. First thing is this. What's the change in anything? Oh, well, let's put this up in the corner. Remind me, what's the definition of momentum? Momentum's equal to? Correct. All right. Ooh, that's not helpful.
You need your lines up there.
There we go. Cool. Just got to separate them out. All right, so change in anything you said is? So that would mean this is mass times velocity final minus velocity initial over time. Next thing I'm going to do is multiply time on both sides. And while I'm multiplying time on both sides, I'm going to distribute this out. Mass times velocity final minus mass times velocity initial. And like we said a second ago, what is mass times velocity? So this is the same thing as momentum final minus momentum initial. Getting us to the final equation here. And I say final equation because you'll notice I really haven't changed Newton's second law. This is in fact Newton's second law, and yet we give it a different name. Okay, and that's this. Sum of forces times time equals the change in momentum. This, air quotes, new equation is known as the impulse momentum theorem. And like I said, in all honesty, it's really just Newton's second. So a well-discerning and not lazy, but pragmatic high school student would probably say, okay, great, if it's the same thing, why the heck did we make a new one? And that's because it does something a little bit differently. Whereas Newton's second law focuses in on an individual object, this starts to look at, let's just kind of put the $10 word out there that we use, collisions. It's colliding. What happens? And to help you out with this, let's imagine real quick, basically the egg drop. Imagine, I don't actually have them, people online, I have two eggs held at the exact same height, okay? And I drop them, okay? Now, they should have the same gravity on them, yes?
Yes.
So when they hit the ground, they should hit the ground with the exact same velocity, yes?
Yes.
But let's say one of them hits the ground, and one of them, I've got like a very kind of a pillow that kind of extends into the ground so it falls the same distance. So one's going to hit the ground and one's going to hit a pillow, okay? Both of them hit the ground with the same initial velocity, yes? And both of them are going to stop, yes?
Yes.
So are both of them going to change the exact same amount of momentum on that collision? Do they have the same mass?
Yeah.
The same initial velocity?
Yeah.
Same final velocity?
Yeah.
So should they change the same amount of momentum?
Yeah.
Yes, they should change the exact same amount of momentum. But obviously, I think you guys are skipping ahead to what the result is. The result is not the same. Even though they change the exact same amount of momentum, what's going to be different for the egg landing on this tile versus the egg landing on the pillow? One's going to be one's going to break, and the other one isn't. Why? Take 30 seconds with your group, see if you can't kind of deduce this on your own, and we'll cover it in just a second. Why? All right, sounds like you guys kind of got it. All right, so let's talk variable by variable here, breaking this down. So we just shared that both eggs should change the same amount of momentum, right? Okay. Why does one of them break and the other doesn't? Yes.
It takes more time.
Oh, careful. You're in the wrong variable first. Listen carefully to what I said. Which variable decides whether or not it's going to break? Correct. So let's start there. Why does one break in terms of force and the other doesn't? There's what I'm looking for. Yes, the one that breaks simply had more force on the shell than the one that did it. Now, to the reason why, okay, why does one not break then?
It takes more time to.
More time means you can use less force. Okay, if we have gymnastics or we have cheerleaders that are going to play out on the that are going to play on the basketball court, that's a terrible idea for them to do tumbling just on the basketball court as it stands. Why? Because if their joints come down on wood, it will stop their joints in a very small fraction of a time. So simply put, what do they do to fix it? What's that? They put on a mat. And what does the mat do? Well, simply put, the mat does this. It starts to put a force on their legs earlier. Now, the amount of time that it takes you to stop when landing on a mat is not that much different than the concrete, but the times are so small that what you're really looking at is a ratio. If their legs land and stop in 1 millisecond on the on the wooden floor versus they put down the mat and now it takes 10 milliseconds, you go, well, 10 milliseconds isn't very long. Yeah, but it's 10 times bigger. So if this time is 10 times bigger, what happens to this force? 10 times smaller. It's essentially exactly what your seatbelt does. Can the steering wheel stop your face just the same as the seatbelt? Sure. It takes a very small fraction of the time for the steering wheel to stop your face.
So what does the seatbelt actually do? By the way, anybody having actually gotten in an accident, hopefully that's not any of you. If you don't know this, you will walk away with bruises. You will walk away hurt from the seatbelt. But the most important thing about a seatbelt is the fact that you will walk away more than likely, not exactly the state that you walk away. It takes the time that it takes to stop, which is small, and doubles it, quadruples it, 10 times it, 20 times it, so that you take the force and do the exact opposite. All right, a few things about this equation, we'll move on. You'll notice that this says the impulse momentum theorem. On the right side of this equation, you will notice the momentum, sort of. I'll come back to that in just a second. So if you had to guess what the impulse is. This side right over here is known as impulse. Now, in certain equations, they actually take force and time and make a new variable. None of our texts do, so you just have to understand that impulse is not, listen to this carefully, impulse is not the force. Impulse is not the time. It is the combination of the two of them. So, what are its units? Well, you might already say it's kilograms. I know how the equal sign works. That's not what I'm looking for. What are the units of impulse? Newton seconds. And what are the units of momentum? Kilograms, meters per second. So, well, Spain hours, shouldn't they be the same? 110%. They should. Let's check. What are the units of a Newton, actually? Meters per second squared times seconds. Cancel, cancel. Are they the same thing? Cool. So why can't I just use one or the other? The answer is simply context. Okay? If a problem asks you for what the impulse is, you should use Newton seconds. If the conversation asks you for change of momentum, you should use kilograms, meters per second. Now, are they equal to each other? Yes, 100% they are in that particular case. Okay, so that's impulse. The other thing I wanted to highlight here, kind of pulling this back up to the beginning that a lot of people screw up. Let's see if I can't pull both of them on the same screen at the same time. Yes, all right. What a lot of people will also screw up as they continue into this equation is they will say, hey, impulse says impulse is equal to momentum. No, there's a very important distinction there. Why does that not say that? It says it change in momentum. We have an equation for momentum already. It's right there. Here's the simple understanding and reminder that really impulse momentum theorem is Newton's second law. Spainor is walking across the front of the room. Based on first law, what do we know about his forces?
Balance.
It's balanced, and therefore the sum of forces is 0. So what's his impulse? 0. So what's the change in momentum? 0, which is exactly what we saw here. Does that mean I didn't have a momentum? No, it just means it wasn't changing. So this equation shows us how momentum changes, not what it is. This equation on the top left shows us what it actually is. Okay? Although there was one more thing I wanted to cover. I don't think so. We'll cover more of this tomorrow. I'm going to start and equate a problem. I know I don't have enough time. I'm simply going to set it up so that you can either practice it at home or we can cover it first thing tomorrow. I don't think it's going to take a lot of time. So let's imagine a football player running to the left. Sorry for those of you guys that aren't into football. It's that season and we're talking about collisions, so it kind of makes sense. So let's start off normal numbers here. Help me out. What would be a normal velocity, magnitude, so I guess speed, of a professional football player running at top speed? What's that you say? I think you said 45. Someone literally said that last hour, like right away, and I was about to jump on you the same way that I jumped on Lamar. Like 45. No! Usain Bolt ran a 100-meter dash in like 10 seconds, so he topped out at like 20 meters a second, average 10. No. Okay? So 4 to 5, what do you want then?
Let's do 5 just because.
That's what they did. That's fine. All right. Mass of a football player. Professional one.
100 kilograms.
220.
100 kilograms.
Yes. That's literally what they chose. That's hilarious. All right. Now I'm going to give you some numbers because, number one, you probably don't have context for these numbers quite as well. But number two, I want to show them play out, but I will tell you that these numbers are a little bit off. I'm going to tell you that the sum of forces is 100 and, what did I say? I think I went, I do 104. I'm trying to remember what numbers I used. My apologies.
It's okay.
Appreciate that.
I don't forgive you though.
Well,
I'm sorry.
yeah.
Wow.
200. Okay, it was 200. All right, 200 newtons to the right. 200 newtons to the right, and we're going to apply that for 1.7 seconds. Give me 2 seconds and I'll finish up. This time, I want to highlight ahead of time how ridiculous this time actually is. I drew it up to 1.7 seconds so that the numbers are not really that bad, but keep in mind that when I say 1.7 seconds, that would be how long the collision actually took place. So to hit for 1/1000 and then 70% of another, that's a hit and a half, as well as that's probably not going to happen. It's going to happen a lot shorter. So I could get the same result. This is also to highlight this. What could I do if I wanted to make this a more realistic time? If I made this like half as big, simply to get the exact same result, I would double the force. The only reason I'm not is so that you can see the numbers work a little bit cleaner right now, but no, that's a little bit off. We'll finish this tomorrow. The question, by the way, if you want to finish it using these numbers is, what is the final velocity of the football player after this collision?
I also have to ask.
Please do.
Is the momentum chapter
Yeah.
conveniently timed with football season?
No, it's something, and the egg drop at the exact same point in time. That was no accident as well.
Mr. Spinner, you're lying. Do you watch it now?
Do I know?
Do you watch it now?
I do. Well, hold on a second.